analyticity of f beta h for h different of 0. And this is in arbitrary dimension. Okay, this is important to say because so far, each time we had used complex analysis, it was in dimension 2. So, okay, so what does it mean? So what are we going to prove? Well, we are going to prove that for every h in R, there exists delta h, which is positive, such that for all u in R, u smaller than delta h, we have f beta h plus u, which is equal to the sum from n equals 0 to infinity of 1 over n factorial d n h f beta h u to the n. Okay, so what's implicit here is what I'm saying is that f is infinitely differentiable in h, and its Taylor series converge with some positive radius of convergence. And okay, basically you can find two proofs of this in Friedli and Velenik's book. And mostly the difference between the two proofs is on the value of delta h here. So what we are going to prove is that you can take delta h is equal to h over square root of 2. And it turns out that, okay, there exists a proof which is a bit more complicated, and that gives you delta h equal to h without the square root of 2. Okay, but as far as the properties of the Ising model are concerned, this delta h doesn't really matter, because one implication of this is that the magnetization varies smoothly, okay, when we vary h outside of 0. Okay, so what do we need to prove this? We are going to use complex analysis. Well, the idea is that, well, complex analytic functions, they have really some kind of rigidity, which makes sometimes convergence theorem easier to prove, okay? Okay, this is basically what we are going to use, like complex analysis magic. So I'm going to define a set D, which is, okay, it's not exactly a domain, it's a union of two domains. D will be the set of x plus yi. So x and y here, it's implicit that they are real numbers, okay? So it's a set of complex numbers for which the real part is larger than the imaginary part in absolute value. So D, it's this H region of the complex plane. Okay, and well, let's separate it in two. So we call the red region D plus and the other one D minus. Okay, so the theorem we are going to prove, in fact, which implies this, is that the function h f beta h defined on R admits an holomorphic extension on D. Okay. Well, holomorphic for me it's just synonymous of complex analytic. Okay. So well, in particular, I mean, if it admits an analytic extension, it means that it's analytic on the real line. And if you want to know the radius of convergence here, you take an h here, okay? And basically you have to kind of know what kind of ball you can put in the domain. And it turns out that the radius here is square root of h over square root of 2. Okay, so it turns out that, I mean, you can in fact prove that analyticity holds on this, on the full place minus this line, but I don't know. I don't think it's worth the hassle to prove this more precise results because I don't know. I find this considerably easier. Okay, so a first remark is that since f beta minus h is equal to f beta h, we can restrict the proof to D plus. Okay, because for the analytic expansion on D minus, you just take, well, your holomorphic function and you just apply it to minus. To have the extension here, you just take the extension here, and here you apply it to minus h instead of h. Okay. And this is just because, I mean, when you define the free energy, you can take any boundary condition, and we have seen that when you have free boundary condition, the partition function is invariant under the symmetry H gives that maps H to minus H. Okay, this is just by you can just seize it by just flipping all the spins when you make the sum. Okay. Okay, so what's the most naive idea you can come up with when you want to prove something like that? Well, the first thing you can remark is that, today we are going to work only with free boundary conditions, so I will not write the 0 here. I will just write V. Okay, so this is just a partition function for free boundary condition. So I cannot define the Ising model for complex H, but I can define the partition function. Okay, because I just write the same formula and it makes sense even if H is complex. Okay, so this is the sum over sigma in omega lambda exponential sum over xy in E lambda sigma x sigma y times beta. Okay, and here, okay, it's important in our theorem that beta is positive. n plus sum from h in lambda h. Okay, I can put it here. Okay. So then what I could try to do is take the log of this. So I have to be a bit careful here. So dividing by lambda is not too tricky, but I have to be careful when I take the log. Okay, let's discuss that later. And then we can try to make lambda go to ZD in the Van Hoff sense and try to see if this has a limit. And then naturally, you would expect that this limit should be the holomorphic extension of your free energy. Okay, so the first issue here is that, of course, the complex exponential is not injective, so the log of the is not the log of a complex number is not something that is well defined, or if you want, it's only something which is defined modulo 2I pi z. Okay, so it turned out that well, under some condition, you can define unambiguously the log of an holomorphic function. So this will be the first. Okay, today we are going to revise a few results of complex analysis. So some of them you might know them already. Some of them you might see them for the first time. Yeah, I will give an idea of the proof of this one, and for the rest, it's more complicated, so I won't give proofs. So, okay, what's the result here? So let's D be a simply connected domain. And F from D to C, an holomorphic function. Okay, which doesn't cancel. Okay, and let x0 and y0, okay. Maybe you want me to call this Z, I don't know. Z0 and, okay, C0 be such that f of Z0 is equal to exponential C0. Okay. Then there exists G from D to C such that for all x in D, exponential gx is equal to f of x, and gx0 is equal to c0. G, okay. Okay, so the idea is that you can take the log of f of z as soon as f is defined on a simply connected domain and doesn't cancel on it. Okay, and how do you make such a construction? Okay, so I mean, naively, this is something you can always do, you know. If you fix a value at some point, basically, and you know that everywhere, I mean, like log of f of z is defined modulo 2 IPZ. So in the neighborhood of this point, like the element of this that fits is kind of determined by continuity. So what you have to make sure is that different choices of paths for going to a point lead to the same result. Okay, so the important thing is that this function is analytic. Okay, in particular, it's continuous. Okay, so the idea is that we are going to take G, which is just a primitive of f prime over f that is equal to C0 at Z0. Okay, so we take G of Z. It is equal to the integral from Z0 to Z of f prime of u over f of u du, okay, where here the integral is taken over any path from Z0 to Z. Okay, and the reason why the integral doesn't depend on the choice of the path is that if you take two paths, basically, and you take the difference between the two integrals, you get the integral along this contour. Okay, so you are going to take the integral of an holomorphic function over a contour which is contractible, okay, because our domain is simply connected, and therefore it's equal to 0. Okay, and okay, so why is the exponential of g of z equal to f of z? Well, you just have to compute. Why do you get this? Sorry, here it's C0 plus. Okay. I don't think it's complicated then to check that g is equal to the exponential of g is equal to f. But let's not go into this because I'm not sure I can do it now. So. Okay, but I mean, basically this is reasonable. Well, you see that, I mean, okay, here, this assumption is crucial. Okay, if this is not true, clearly the theorem is not true. So for instance, if you take D is equal to C, F is equal to the identity, well, this theorem is not true. Okay, because if you try to define log z, okay, if you take it, sorry, C is equal to, D is equal to C minus 0, and f of z is equal to z, okay, because this thing is pretty much mandatory to have this. Then it doesn't work, because if you try to define log z on the full complex plane, basically you will run into continuity problem, okay? I mean, if you want it to coincide with log on the real line, basically if you start to go from there, you will want this to be equal to, well, you will want the imaginary part of this to be I pi, and if you go this way, you will want it to be minus I pi, and you will get in a contradiction. So we'll have to choose basically a line somewhere where it will not be continuous. So you will have to basically slit your domain so that it becomes simply connected. Okay. And so basically, this assumption also tells us that if we want to follow that plan, there is something important that we have to prove. And this will be actually the main task of today. I mean, the rest is just remembering and applying complex analysis results. So the important thing that we will have to prove is the following. That, so with this definition, okay, so here H is in C, what we have is that for all H in D, for all lambda Z lambda beta H is not equal to 0. Okay, so I will prove this at the end of the lesson, and we will try to move on from here to see what we need to do next. So, okay, so let's admit that this thing is true. So, okay, and let me just say on D plus, it's also true on D minus. But, so if star is true, then what do we have? Okay, then we can apply the proposition to f of z is equal to log z beta h, okay, and c equal to d, d is equal to d plus, and z0, okay, being some arbitrary point on R, okay, and c0, well, being just the real logarithm of this. Okay, and if I do this, I obtain a function g, and with some abuse of notation, okay, we write log z beta lambda beta h for the function g, which is obtained. Okay, so remember that even though we write this, this is not at all the composition of two functions. Okay, this is not the composition of a function which would be the complex logarithm with z. Okay, this is just an analytic function which is log zh. Okay, and what we can check, okay, is that when h is real, this notation corresponds to the other definition of log, which is just take the log of z, okay, which is something that makes sense when h is real. Okay, so how do you see this? Well, basically, this relation tells you that this is true modulo 2i pi, 2i pi, okay? This specification here tells you that this is true for one specific point on the line, and then continuity allows continuity allows you to conclude. Okay, so here, what we are using is really the fact that the intersection of D with the real line is connected. Okay, like if you had a real function here, and then you wouldn't be able to make sure that these two things are. Here we are really using the fact that you can go from a point on the real line to another point on the real line, staying in D. Okay, this is important because you're using just continuity of G. Okay, so I have a function which is the logarithm of my partition function. And furthermore, it coincides with the real logarithm on the real line in the sense that there is no imaginary part. And yeah, this is just by the fact that it's satisfied at one point, and then it has to be satisfied everywhere else by continuity. Okay, because if not, it would make a jump of size 2i pi somewhere. Okay, so far is everything clear? Okay, so now we have to try to prove convergence of this, and this is where it becomes kind of at first it becomes it's mysterious how to do this, because if you remember, what we used when H was real was really something that relied on H being real, in the sense that we used superadditivity, which is something which is which is based on the fact that there is an order on R, and on C you have nothing of the kind. But it turned out that here what will help us is like the fact that there is not so much degrees of liberty to define an holomorphic function. Okay, so basically, in order to prove that a function converges, it's sufficient to prove that it converges somewhere on the domain, and that in the remainder of the domain, it's bounded. Okay, so the reason why is that basically, okay, philosophically, if your sequence of function is uniformly bounded, you will be able to extract a converging subsequence. Okay, and if it converges on some subset, which is not too small, okay, then it will give you the uniqueness of the possible limit point. Okay, and therefore it tells you that it converges along all subsequences to that limit point. So this is Vitali's theorem. And this tells you the following. So if D belongs to C is simply connected, and H is included in D, and has a clustering point in D. So what does that mean, that H has a clustering point in D? It just means that there is a point in D which you can approximate by a sequence of points in H. And this sequence, I don't want it to be stationary. So, like, there exists H n, a sequence of distinct elements of H. Okay, so there is no repetition in my sequence such that limit of Hn belongs to D. Okay, so in particular, I mean, any uncountable set H would do. Okay, some countable sets would do as well. And we are going to use it for H, like some segment on the real axis. So, okay, so what's the theorem? So if Fn is a sequence of holomorphic functions satisfying. So two things. So the first thing is for all v in H, limit when z tends to infinity of Fn of z exists. And two, the supremum over z in D, and the supremum also over n larger than 1 of Fn of z is finite. So another way to enhance these two conditions is to say that Fn is uniformly bounded, and the other thing is that Fn converges on H. Then what's the conclusion? Then there exists F holomorphic such that Fn of z converge to F of z uniformly. Okay, and this is Vitali's theorem. Okay, so in order to prove that something converges, you just have to prove that it's uniformly bounded and to prove that it converges somewhere, which is not, that it converges on a subset which is not too small. Okay, so let's try to apply this to our problem. Okay, first, if I want things to be bounded, it's better for me to restrict myself to a bounded subset. Okay, if H is large, the free energy is large. So I just define dk to be the set of H in D plus, okay, the set of X plus Yi in D plus such that X belongs to 0K. Okay, so I'm just, if I can prove, convergence in this triangle for arbitrary K, then I prove convergence on the whole D. So there is no problem. Okay, so let's restrict to this. Then, okay, the convergence for H between 0 and K, for H real, it's really the convergence to the free energy. We don't have so much to say about it. So what remains to prove would be that 1 over lambda log of Z, lambda, is uniformly bounded over dk. And the problem is that we don't really know how to do this. But there is something we can prove, which is the boundedness of the exponential of this. Okay, so we are going to consider, okay, Fn, okay, which is just the exponential of 1 over lambda n log z lambda n beta h. Okay, so this has been defined. This is a complex number. We are taking the exponential of a complex number. This is not a problem. Okay, we are dividing a complex number. And here, I mean, lambda n is just an arbitrary sequence that converges to ZD in the Van Hoff sense. Okay, so clearly, we have Fn of h, which converges when n goes to infinity, to exponential f beta h for h in 0k. Okay, so this is our state h here. Okay, and now we just need to prove that Fn is uniformly bounded on dk. And we will have, okay, and then we will have convergence of this, and then from the convergence of the exponential, we still have to deduce the convergence of this. Okay. Okay, so now the boundedness is not so complicated because there is no difficulty in computing the modulus of this. Okay, so the modulus of Fn of h, it is equal to, well, the exponential of the real part of log of z lambda n beta h. Okay, and because we know that the exponential of this is equal to z, this means that the real part of the log has to be the log of the modulus. Okay? I mean, this specification here, it already, it already defines unambiguously the real part of G. It's just the imaginary part that, okay, so this is equal to exponential 1 over gamma n log z lambda n beta h. Okay, which is simply equal to z lambda n beta h to the 1 over the cardinality of lambda n. Okay, so we just have to bound this modulus. This is a sum of complex number. We can bound the sum of the modulus, and this should be fine. So what can we say about this? Well, this is smaller than the sum over okay, now we can bound this by +1, we can bound this by +1, and we get that all of this. Well, it's smaller than the cardinality of lambda times, well, this is just the cardinality of omega lambda. Then we get exponential beta times e lambda, and then we get the real part of h. So real part of h is smaller than k times lambda. Okay, and well, clearly, if you take this to the power 1 over lambda, then you get something which is uniformly bounded. Okay? Just because, okay, maybe this is smaller than 2 to the lambda. I think this is smaller than d times lambda. Okay, so you have your explicit uniform bound on this modulus. Okay, so now as a conclusion of this, what you get is that the limit when n goes to infinity of fn of h exist, and we call it G beta of H. The last step we need to do to conclude is to define the log of this. Okay, and to define the log of this, so this is true for all H in decay. I mean, the convergence holds for all H in decay. Since this holds for every K, okay, then you have this convergence on all, on D. Okay, and then the next step is basically to show that we can take the log of this. And we will be done. Okay, so to show that we can take the log of this, we have to show that this doesn't cancel. Okay, this is what we need to take a log. Okay, so let's take a small break here, and we will resume in 5 minutes. what we've done so far is we have defined an analytic continuation on D of the exponential of the free energy. And basically, to conclude, we need to show that we can take the logarithm of this, which is basically saying that this analytic continuation of exponential of f, which I call g, does not cancel on d. Okay, we will use, again, some magic result from complex analysis. Maybe, I don't know, maybe it's the one that the two first one I presented, it seems that I understand rather well. This last one, I would have to see the proof again to understand really how it works. So let me mention that we don't really require it. So if you remember, what we wanted to show, okay, is that basically the free energy is analytic on the line. Okay, so we don't really need to have an extension on D, we just need to have an extension on a neighborhood of the line. Okay, so for each h in R, there exists epsilon h such that G beta z does not cancel on the Euclidean bow of center h and of radius epsilon h. Okay, this is just by continuity. Okay, so now if you define D to be the union over H in R of BH epsilon H, well, then you get a simply connected domain on which G does not cancel. And on this, you can define the log. Okay, so if you're not interested in having the extension of the free energy on the whole of D plus, then you don't need this last bit to conclude. You can conclude just using this. Okay? We define f beta h Okay, I mean, when you define log of G beta H, basically you're fixing a primitive, you're defining it modulo a constant, so you just fix that constant so that it's real on the real line. Okay. Well, the idea is that you can define the free energy on the whole of D plus, so let me explain why. But basically, if you're just interested in regularity and the free energy on the real line, maybe this is sufficient. Okay, yeah, I mean, in the real line also, this does not give you any information on the radius of convergence. So, you take a domain which is connected. Here you don't need simple connectedness, I think. Fn, a sequence of holomorphic functions. Which doesn't cancel on D. Okay, then what we have is that Fn on D converge when n goes to infinity to Fz uniformly in D. Okay. So these are the assumptions. So imagine that you have a sequence of holomorphic functions that don't cancel, that converge uniformly. Then either f is uniformly 0 or f doesn't cancel. Okay, so basically a sequence of functions that doesn't cancel when it converges as a limit which doesn't cancel. This is clearly not true for any regular real. I mean, you can find counterexample for real valued functions that are infinitely differentiable. So this is really analyticity that makes this work. I don't know. It's a beautiful result, but this is where my intuition stopped because I don't practice enough complex analysis. But maybe yours is better. Okay, so basically you're applying this result with this d equal to dk, fn being equal to the fn we had defined before, which was just the exponential of 1 over lambda n times log z lambda n beta h. And then you know that, from our previous theorem that the Fn converges uniformly on D, and therefore from this theorem, because you know that Fn doesn't cancel, you know that the limit doesn't cancel because you know that this is not true. Okay, and clearly here the two things are possibilities because if you take, I don't know, Fn is equal to 1 over n, then the limit is 0. Okay, so we are basically done, except that we have admitted this important part here. And this part is really needed. I mean, you can't say, okay, maybe this is not necessary because we know that, well, this thing does not cancel on the real line, so there is a neighborhood on the real line on which it doesn't cancel. Okay, the reason why you can't do that is because the neighborhood of the real line you will find, it will depend on lambda. And you need something that does not depend on n, okay? When you need to show that this is true, basically. You don't really need to show that it's true on D+. You would need this only on the neighborhood of the real line if you're only interested in the fact that the free energy is real analytic. But yeah, you need a neighborhood that does not depend on lambda. And this makes things difficult. And it turns out that It's not more difficult to prove things on D plus than just on the neighborhood of the line, of the line. Okay, so let's try to prove this. So in general, inequalities are easier to prove than, okay, inequalities in general are easier to prove than anything else. So the idea is to put oneself in a framework where quantities are real valued. So what we are going to show is that the modulus of Z does not cancel. And the modulus is not really a nice quantity, so we are going to be looking at the modulus square. Okay, so if you look at the modulus square, it is Z lambda beta H times Z lambda beta H. And this is something you can write as a double sum. Okay? And because this is real, okay, and non-negative, okay, we are going to try to show that this thing is strictly positive. Okay, so what is this double sum? So, well, here I sum over sigma, and here I will sum over sigma prime in omega lambda. Then I get exponential beta sigma x sigma prime x. Beta sum over xy in E lambda, sigma x sigma y, plus sigma prime x sigma prime y. Okay, and when I look at the magnetic field part, well, I have to take the conjugate weights, okay, for Z bar, and well, the conjugate of the exponential of H, it's the exponential of the conjugate of H. And the conjugate of the product is the product of the conjugate. Well, so in the end, this is what you get. Okay, and now we want to make a change of variable in this sum. Okay, so the idea is okay, basically, if you look at sigma x prime, okay, this is something that belongs to minus 1 to the 2. We want to replace it by some angle theta x, okay, that is just a multiple of pi over 2. Okay, so how do we do this? Well, we just take the angle theta x, which is such that cosinus theta x is equal to theta x plus theta prime x over 2, and sine theta x is equal to theta x plus theta prime x minus theta prime x over 2. Okay, and this is, if you impose that theta x has to belong to this set, basically you have something which is bijective between this and this. Okay, so this is really just a change of variable in the sum. Okay, and now we have to try to find how to rewrite these things, the theta, well, all that appears in the exponential, how you can rewrite it in terms of theta x. Okay, so here, I mean, you can check when the two things are equal to 1, theta x is equal to 0. I mean, basically, you know, this is theta x, theta prime x. You can take 4 values. And theta x is more or less related to the angle you have here. So it's probably the angle minus pi over 3. Or, I don't know, minus the angle minus pi over 3, something like that. Okay. So, maybe the easier thing is the part with the magnetic field. So let's say that H is equal to A plus IB. Okay, and what you have is that A is larger than B, which is larger than 0. Okay, this is just because H is in T plus. Okay, so what we have is that sigma x H plus sigma bar x, sigma prime x H bar. This is equal to A times cos theta x plus, 2A times cos theta x plus 2IB times sin of theta x. Okay, I'm just here I have A times theta x plus theta prime x and IB times theta x minus theta prime x. So, and now this is just, I can write it as, okay, this is just exponential I theta x plus exponential minus I theta x. This is just exponential So what we get is, okay, the 2 has to be included in here. So what we get is just A plus B A plus B exponential I theta x plus A minus B exponential I minus I theta x. Okay, and the place where the condition H belong to D will come is just these two things here, A plus B and A minus B, they are positive. This is the only thing we need. Okay. Now let's go to the theta x, theta y plus theta prime x, theta prime y. So this thing is actually equal to theta x plus theta y times theta prime x plus theta prime y plus, okay, then I have to put 1/2 in front, maybe. Okay, you see that here in this, when you expand these products, the cross terms, they cancel each other, and the diagonal terms, okay, they are the same, and they are exactly what you want. Okay, so this thing is just 2 times cos theta x cos theta y minus sinus theta x sinus theta y, no, plus. And if you remember your trigonometry, this is just 2 cos theta x minus theta y, okay, which is just exponential I theta x plus theta, minus theta y plus exponential I theta y minus theta x. Okay, so now what we can do is substitute this expression in here and try to see what we get out of it. But okay, so the idea is then to expand the exponentials, then you will get lots of crazy coefficients in exponential I theta. But the idea is quite simple. It's the same we used many times for the spin things. Like each time you have a factor which is sum over x, sum over, if you have a factor sigma x, and in front you have sum over sigma in omega, then you know that your sum is 0 because this when you sum, okay, if you have sigma x and then something that does not depend on sigma x, then basically this factor will make this the sum 0. Okay, just because it's plus 1 plus minus 1. Okay, so here, what we will rely on is the fact that if you have exponential I theta x somewhere, and then a bunch of things that does not depend on theta x, basically just when you sum over these 4 values, you're getting 0. Okay, because you're just summing 0 plus I minus 1 plus I minus 1. Okay, so the idea is that we'll put everything in the sum. We'll expand the exponential. We'll get a sum of crazy polynomials in exponential I theta x. But the thing is that for this polynomial, only the coefficient of 0 will matter because all the other coefficients, I mean, the sum over theta will give something which is 0. Okay, so the idea is quite simple. When you write it, of course, it seems very complicated. Okay, let me just write it. Okay, I will write it here, and afterwards I will erase. So z lambda beta h square. Okay, so this is equal to the sum over. Okay, so let me write theta for the vectors, which is made of all the theta x's. So theta belongs to 0, pi over 2, pi, 3 pi over 2 to the lambda. And then you have exponential beta exponential I x minus theta y plus exponential I theta y minus theta x plus a plus b exponential. So this is the sum over x, y, lambda. This is exponential I beta x plus a minus b exponential minus I beta theta x, and here I'm summing over x and lambda. Okay. So now I'm just saying that this thing is just the same sum over theta. Let's not write the set on which I'm summing. And then I have a sum over n larger than 0. And then I have 1 over n factorial. I'm just taking the Taylor expansion of the exponential. And then I have this. So the sum over x, y, lambda, beta exponential I, theta x, theta y, plus exponential I, theta y minus theta x, plus sum over x lambda, exponential I, a plus b, exponential I theta x, plus a minus b, exponential minus I theta x. Okay. So now let's basically expand everything. So if you expand this product, okay, what you will get is just a bunch of polynomials in exponential I theta x. Okay, and what's important here is that all the coefficients are positive because beta, a plus b, and a minus b are positive. So each time you expand things, you get things that are positive. Okay, so when you do this expansion, then you get, okay, you don't really worry about what the coefficients are. Okay, so let's okay, so let M be a vector. I mean, M is just mx, x in lambda, and it's just the mx is just the power to which exponential I theta x appears. Okay, so I get here some coefficient bm, and I know, okay, I know a few things about bm. And then I get the product over x in lambda exponential I mx theta x. Okay, so here there are a few things to check, and there is one thing that I kind of leave at an exercise because it's not surprising at all, but it's a bit, okay. This one is not a bit annoying to check, but maybe the next one is a bit annoying, I don't know. Yeah, no, so okay, so there are a few things that you can say. So the first thing is that Bm is positive for all m. Okay, it's non-negative for all m. So this is just due to the fact that this thing is just a product of beta a plus b and a minus b to some power, and you have some prefactors and you have some sums. Okay. The other thing is that B0, it is larger than 1. Okay, simply you take n equal 1, and this gives you some contribution to B0, and there are some others that comes from just canceling factors in the product. Okay, and the last one, which might be really important, is that the sum over the BMs is finite. Okay, and this is just saying that you're not making anything wrong in your expansion. Okay, and yes, I guess you can pretty much compute the sum of the BMs. You just replace here everything by 1, okay, and you get the sum of the BMs, I think. So. Okay, I mean, in particular, this tells you that each BM is finite, which is important when you write this, when you're reorganizing your terms. Okay. Now here, when you've written that, you've actually, it's not a very good decomposition because 4 times theta x, it's a multiple of 2 pi, and therefore, I mean, the value of this, it only depends on mx modulo 4. So, okay, so this thing, it's equal to the sum over theta, the sum over, okay, let me call L. Yes, in 0, 1, 2, 3. Well, okay. Maybe z over 4z is better. To the lambda. Well, no, 0, 1, 2, 3 is better. 1, 2, 3 to the lambda. A, L, product of x in lambda exponential I Lx theta x. Okay, well here A L is just the sum over M such that for all L, for all x, mx is equal to Lx modulo 4 of Bn. Okay, I'm just putting terms together. Putting terms that corresponds to the same polynomial here together. Okay, so now I can just interchange the sum. And the important claim here is that if L is not equal to 0, then the sum over theta in 0, pi over 2, pi, 3 pi over 2. Exponential product of exponential I Lx theta x omega, this is equal to 0. Okay, and how do you prove this? Well, you take the coordinate for which this is not equal to 0. Okay, so this is just saying that sum over theta in 0 pi over 2 pi 3 pi over 3 of exponential I theta L is equal to 0 for L that belongs to 1, 2, 3. Okay, which is so yes, I mean for L equal 1 or 3, you're just summing 1 minus 1 I and minus I, and for L equal 2, you're just summing 1, 1, minus 1, and minus 1. So each time you get 0. And here, if you have one coordinate of L which is not equal to 0, you just look at, I mean, this thing is just, you can factorize this sum. This is just a product of sum. You will have one of the factors which is this, so this is equal to 0. Okay, so therefore this thing, well, it's equal to, well, just the term that corresponds to L equal to 0. And when L equal to 0, this is equal to 1. Okay? So you just have to deal with the cardinality of this set here. So this thing is equal to A 0 times 4 to the lambda. And well, we know that A0 is larger than 1. So this is larger than 4 to the lambda. Okay, so it's not only that we prove that that the partition function is different from 0, we really have a lower bound for the modulus that is uniform in H. Yes, and okay, so this is pretty much the conclusion of what I had to say. So but yes, I mean the final observation on this is that like even though there is no physical meaning in looking at a statistical mechanics model with a complex parameter, okay, because when you're doing statistical mechanics, usually, I mean, you're taking Gibbs weight, you're normalizing by the sum to define a probability, so if these Gibbs weights are not positive, maybe it's not very meaningful. But nonetheless, if you study the partition function for the complex parameter, this can yield really interesting information in the real case back. So this is the reason why, yeah, like studying this thing even when the parameter takes a complex value is interesting. Okay, and yeah, maybe one final comment. Okay, so far what we have seen is that basically, yeah, magnetization is basically continuous in this whole region, and there is a discontinuity here, and that furthermore, it's continuous, it's analytic away from the h equals 0 axis. So maybe a natural question is, well, is it analytic at 0 when beta is not equal to, is smaller than beta c? Okay, I mean, here clearly it's not analytic because it's discontinuous. And here, clearly this proof doesn't work, but maybe something else should work. So actually, I'm not sure what the answer. Oh, okay, so the answer is clearly this should be the case. What we did, the high temperature expansion we did, if you just, okay, if you do it the hard way, I think from this you can extract analyticity in H around 0. Yeah, I'm not sure if people can do it until there in all dimensions. So just to say that I think, okay, my hint would be that probably people can do it in dimension 2 and not in higher dimension. So just to tell you that, okay, there are still some relatively basic questions that are open for the Ising model. Okay, so there are like questions that are a bit hopeless, like what's the value of beta c in general dimension? But like even these natural questions, where I think for physicists it should be clear that everything is analytic except away from this singular line. But from a mathematical standpoint, yeah, I would have to check the literature, but I think there is probably a region here where people don't know what to say. Okay, so